We got through so many slides.
Oh, okay.
Meeting
So-
done.
Meeting is starting.
So.
Yeah.
Oh, yeah, thank you.
We'll do it to that.
Like the office. Where's the main ones?
So,
So guess what is shown? I'm going to maybe play it slowly. Look at numbers and the images.
Ooh,
What do you think?
they're pretty. That looks like
Looks like
it's applicable to me.
We
Because
looked at things like that before.
it's the Slater determinant, or it looks like it,
Okay.
but that's not like any.
It looks similar, but right now, okay,
They look like orbitals.
okay, better. Oh, which orbitals?
The
No,
first one looked like an S because it was a sphere.
Mhm.
and 2 and 3. Oh, because once we get past 6, it's gonna go into the D. That's my prediction. Never mind. There's D.
No, this looks like S2,
That does okay.
Yeah.
like positive and negative. Oh,
Oh,
sorry, it's
sure.
start to look. The 4 over here. No,
Oh, sure. Okay.
next.
There we go.
This looks like D, and this is a rotated D, right?
Yep.
And this like
F.
P2, P3. But it's more harder to recognize. This looks like F, and then it goes crazy after this.
The G orbitals.
Okay, so you cannot imagine that it is not a hydrogen orbital. So this is eigenstates of two coupled oscillators from Patricia's project.
Fun. How do you interpret all those fun little colors?
They look kind of like a kaleidoscope. Ooh.
Oh, I love kaleidoscopes.
Trippy. Oh, I saw
Yeah,
one went to my first rave.
If there's like two distinct shapes like that, like orbitals, I guess, but only one of them is
Congratulations.
red and yellow and stuff, why would the other one not be that way?
Okay, thank you. Right, I was going to ask Patricia how she interprets it, but you did her job. So, what do you think? What are solid black and this colorful things?
Electrons.
Well, she's working on interatomic bonds, quantized vibrational motion, but it is this. What's the difference between these two shapes, the two objects?
I think the lines, I forget what they're called, but they look like these figures of physics where
Like
any point along that line has the same potential.
force lines. Okay, isosurfaces.
Yeah.
Something like. Okay, but what's the difference between black and colorful? Like, does black ever have nodal points or nodal lines, or it has the same sign? Patricia?
I think the black has no line.
Okay, so it is concentric circles all the time. It's just center changing. And what about the colors? Why?
I feel because the energy around the non generates.
Like, if you have one-dimensional wave packet, what do fringes mean?
Fringes.
Fringes. Fringes, yes. In the waking up in the middle of the night and telling fringes are a signature of
Fringes are a signature of what?
let's bring quantum theory to the level of kindergarten. No equations, only fringes
Okay.
and pictures.
Eigenvalues space.
Like, who has fringes? Does ground state has fringes?
No.
Okay,
That's a good question.
okay, let's answer to Patricia. What are fringes?
It's like the thing at the left side of your paper when you pull it out of the notebook. Those are your fringe.
Oh, it's a little
Wrinkles?
The little
Those curly
squiggly,
bits.
yeah.
wrinkled. Like if,
Was,
like if Patricia ripped this page out of her notebook, the little like curly bits. Oh, but I don't think that's what we're thinking.
How about oscillation?
Oh, what? They're
Oscillation.
oscillations,
Oscillations, fringes, wrinkles. Wait,
wrinkles in time.
You have to-
if I do like, look, stop. So, Fred, what is another line is
Right down the middle where they,
across,
yeah,
along the line x equals y. And if you go across, if you go perpendicular to, like,
Fringe.
yes, and if you go here, like there is a plus and there is a minus here, right? And if you go through dynamics for a longer time, you will see that it will show areas of pluses and minuses, same like wave packet changes.
so the fringe like separates like the different charges or what?
No, charge is the same charge, same particle. But which particle has more, which wave function has more fringes? A slow moving particle or a quickly moving particle? So,
More
Then
fringes, faster moving particles.
okay, I knew you know it in the middle of the.
So smart. This
S
is
plus one.
Plus one, yes. So fringes are a signature of like, velocity, momentum. And if you take,
speed.
right, if you take derivative of the wave function, you get momentum, right? Derivative of space. So momentum derivative will tell when you have fringes, right? So what's the difference in the colorful things?
The speed.
So, but the black one also moves.
Oh, is that like electric? One second.
What, like,
Is it?
I feel it's just oscillation.
yes, but if wave packet is moving, if you track wave function, real or imaginary, it will have positive and negative values. If you take absolute value squared probability distribution, it will be always positive.
Yeah.
So by looking on this figure, a trained physical chemist should say it is the same object. Wave function itself is colorful and absolute value squared probability distribution is black. So it's same, their center moves coherently at the same point. It's just different ways to represent the wave function. Okay, make sense?
Yeah.
Okay, we are good with fringes. What do you think about this? And we are starting the actual lecture. What do you think about this stuff? Do you like it? Do you hate it?
P branch, R branch.
What is V first?
Or no? Well,
Is that a V or is it the mu?
I
Bottom.
frequency?
Yeah.
oh, yeah, well, but that's not.
And
not the same
look
thing that's
here,
up there.
like page 35 CL. I'm asking you what is page 35 CL.
No, I'm looking at it on my phone so I can zoom in on things because it's hard to see on the board. It's blurry.
So you should study. I will try to assist as much as possible, but there is not much semester left. But you should study this subject if you want to please Dr. Hardy. because
Hirschberg?
yes, because of his
There you go.
professional training. It is language that he speaks.
Fluently.
Exactly. So let's decipher what this is. And my plan is not to completely answer this question today. We will provide only foundations, and on Monday we will complete it. But what do you think? Just describe by words.
I'm not allowed to think.
By the power given me by administration of NDSU,
I was told,
If you-
I consecrated you with the permission to think.
listen, consequences are on you then.
So, like, how would you describe the lower panel? If on the x-axis are frequency, not Fred, but Frec. Frequency on the y, it is intensity. This unreadable thing is intensity. So how do you call like a figure, an object, when you have frequency and intensity on two lines? What?
So it kind of,
If you have frequency, intensity, and then something.
it kind of reminds me.
Oh, no. Wait. Intensity as function of frequency.
It kind of reminds me of like an IR graph,
IR graph, good. MR,
like Fourier transform.
you all are good. You all are correct. Anything else? So IR and MR, you
Speed of light. Spectrum.
yeah, start two lessons were correct.
Spectroscopy.
Okay, spectra, right?
Oh, yeah.
Okay,
Sorry.
spectra.
Thinking. No,
Now, in which spectral range do you have like visible, UV, NMR?
there's just an angle. Like, do you mean like a wavelength?
Wavelength or frequency?
Like,
8,000 inverse.
I was gonna say like 10 to the negative like 9 to like 10 to the negative like 5. That's just
You're speaking in wavelengths.
wavelengths.
It's cool. It's really cool. Nanometer. You're speaking in language of nanometers.
Yeah.
Good.
No, I was speaking in terms of
Nanometers. Like 10 to the minus 9 meters is nanometer. And then you go from 10 to the minus 9 to 5, it will be like 1, 10, 100,
Yep.
1,000 nanometers. UVVs is like 500, IR more than 1,000. Good. And inverse centimeters, visible is about 20,000, and about 3 to 1,000 is infrared. Okay, so on the bottom is a spectrum. What is on the top line? Top panel. Yes, great energy states. And so those are energy states. And what are the arrows mean?
rise.
Transitions between different energy states, right? So I see your skills and training. The other unanswered question is energy states of what? Of which degree of freedom, of which molecule?
Inch 35 CL.
Which is?
Hydrofluoric acid.
Yes, with specific isotope
35.
of chlorine. Because chlorine has two abundant isotopes.
35.
It looks like it's.
No.
Yeah, that's him saying it.
Okay,
Okay.
now let's decipher it further. Which energy levels of hydrochloric acid are we looking at?
All of them technically, right? Because the arrows correspond to like the energy states.
Ground states and the first state side.
But there are like 100 states, or at least a couple thousand. If so, let's just depart our train in the right direction. The electronic excitations UV, like hydrochloric is transparent, means it is first excited will be in the UV range, right? It's transparent. So, and the frequencies here are fractions of electron volts, then they're more to the infrared. So it's definitely not electronic radiation. Now, which degrees of if you keep this HCl molecule in the ground electronic state, which degrees of freedom are available? Yes. How many vibrational degrees of freedom is there?
One.
Yes. Okay. How do levels of quantized vibration space from each other? What is the energy of if you have E sub mu for vibration? Would you agree that it is not bar I used? Okay, like H bar omega mu plus 1/2. Do you remember, right? Yeah. Which means that energies with nu equals 0, mu equals 1, mu equals 3 are offset by the same frequency, right? Do we have equivalent offset here? Do we ask the classmates?
We have equivalent offset.
Please,
Is it like
what is an offset? It's Patricia question.
Oh.
It is not like it's not standard word for everyday language. What do you understand under offset? I learned this word while being a postdoc. I didn't know it before. So, what is offset?
Who are you asking?
You guys, you're
Or Patricia or something.
no, Patricia.
Anyone can answer.
Yes.
Sam, take it away.
What's
Offset.
what is the offset?
Teach me the language. What is offset?
Offset.
Like you have your origin,
Mm-hmm.
Yeah.
and then you are off the origin.
It's like the space between like your reference point and
Yeah, like I
another
have to
point.
offset correct things that I plot if it like shifts away from the baseline that I have.
Okay, so for harmonic oscillator, which is any vibration, the offsets are equivalent, right?
Like,
It is the same offset between all levels. Right? But what are the offsets here? It is small energy, then bigger, then bigger, then bigger. So is the offset the same or different? Different. So is it oscillation?
What?
Is that's okay. It's the main reason why we interact with Patricia, because I don't understand what she speaks, she doesn't understand what I speak. We need to work as a team. So if the offset is not equidistant, then it is not an oscillation, right? So which degree of freedom can it be? This is a big puzzle, and it will motivate our lecture that we have only 20 minutes of. Huh? Translational can be infinitesimal. It has continuous spectrum, right? If there is no box, it can travel with any velocity, and levels will be continuous. But I like very much your style of thinking. Your train has departed in the right direction. Now, we have excluded vibration, we have excluded translation, we have excluded electronic degree of freedom. What else is left? Huh? Please use your the permission to think that you have been granted.
I don't know.
Then think about it.
You do not need to know anything.
What states we did?
We need only thinking, no memory, except playing with in the middle of the night.
So what are,
So we have diatomic molecule,
yes,
H35Cl.
yes,
We know that it is a spectrum.
yes,
Spectrum is a transition between different energy levels.
sure.
What is the nature of these energy levels? We exclude, you can give the right answer anytime.
Well, then keep going, because now
You can even give the wrong answer.
I was I guess I don't entirely understand the question quite yet.
Okay.
It's so, we're looking at the spectra of vibrational frequencies, which is the bit like energy levels.
Yeah, it's remote vibrational.
Okay, so we remove vibration,
We remove vibration, we removed electronic,
okay?
we remove translation. Ah, what?
Rotation.
Yes. Patricia, did confirm her high title of great experience. Now it is your duty to explain what is rotational degree of freedom, or ask if everyone understands it, and please lecture us.
Rotational degree.
That's it, Patricia.
So what's that?
Ah. I do not have a click source of all.
Alright,
Just something. You can just show it with hands.
Rotational, like, rotational degree of freedom. Rotation, like, trying to rotate.
Yes,
well,
yeah, correct.
I was gonna say, rotational degrees of freedom.
Let's show all of us should show by like, if we descale quantum theory from graded and undergraduate level to kindergarten, we should explain what is rotational degree of freedom of H35Cl by our hands without saying anything.
Is that right?
It's not wrong, but like, okay,
They don't want
please show me H35 HCl molecule.
Oh, what?
Like, bottom.
He's doing.
This is
That's, huh? So,
Yeah, whip that
No,
yes, can you increase interatomic distance a little bit? Okay, and your small fist shows H, your big fist shows Cl.
yes.
Oh,
No,
really?
you can easily show the oscillation, vibrational equilibrium, right? Vibrational, show. Same. Translation, like, and now show rotational. No.
like this. Well, on the bond, you
Yeah,
add
we need that.
like this.
No. You are great.
Wait, is it like this?
No.
It's the bond rotating, right?
You get perfect grades and knowledge at the undergraduate college level and graduate, but you fail kindergarten chemistry.
Rotational freedom is gonna be based on the atom being able to rotate on the bond.
Right?
You're telling me I'm wrong. So then please enlighten us.
No, you should discover it yourself.
Rotational
Okay.
freedom.
You just not about what are the different ways that it could be rotated.
Yes. Okay, much better.
Okay. Oh, okay.
Okay,
Okay.
so the vector connecting first and second atom makes circles. Okay,
Okay.
yes. Now you pass kindergarten chemistry. Yes, I like it. So now, what is the subject of our this lecture and next couple?
Slowly slipping into insanity.
No, rotation.
No, we're talking science.
Science is just a made up thing.
Rotational degree of
Everything
freedom.
is a made up thing. They're all
Okay.
made of atoms.
So, rotations do have a lot of similarities to what we did before. So before we considered only three models. Which one?
Atom in the, or atom in free space, atom in the box, or particle in the box, and then
Harmonic oscillation.
harmonic oscillation, yes.
Perfect.
I do remember it, Patricia. I don't know what you're talking about.
Now, which of them may have analogy to
Harmonic oscillation,
yes, but which has even better,
particle in the box,
and which has even better?
I was
particle
thinking
in free space.
space.
Yes. So, why free space is so near and dear to rotation?
Because you don't have anything constricting.
Yes. So, When Sam is correct, not when, since Sam is correct. So since Sam is correct, nothing restrains this rotation. They are pre-rotation. No one can stop them, right? And later on, later on, you'll find that they have some levels, but if we do have particle in a free space, it can move slower or quicker in positive or negative direction, right?
Yep.
And measure of the motion is, how do you quantify motion?
Quantified motion.
Yes, like I'm driving.
Speed.
Yeah.
Your miles per hour, meters per second.
Since time is correct. Momentum quantifies motion. Okay, higher momentum, positive, negative, right? Can we quantify motion if it moves on circles?
Technically, yes.
The momentum is always changing.
It-
right?
Like if you
It's
have,
changing direction.
So,
if you have ISS. which
The
is-
International Space Station.
I was thinking of full suspension.
So we know where. Still in high school.
So when ISS orbiting the globe, right?
Yeah.
Likely it goes with the same absolute value of momentum, but it just changes direction. But how can we quantify rotational motion?
By putting a number on it.
Angular.
You are a great philosopher of the past and future. Yes, but which number? Like,
27.
What would you say? Huh? When you're drive cars, right?
Yes.
If you have,
I get behind a wheel, I don't really know if I consider it driving.
so what do you see on your like board, on your panel?
Lots of
There
wacky
are
wheels.
the speedometer and
Which is
the
miles per hour?
Your RPM.
RPM.
Okay, which is,
Your angular
What's
momentum.
the angular velocity?
so what our great philosopher told us? We need to quantify an object, we need to put a number. Which number quantifies rotation?
Remember?
RPM,
Yeah.
right? So rotations per minute or whatever, per second. Good. But then these rotations can, well, we cannot make engine in the car rotate in the opposite direction. We drive back by changing gears, but the H35CL can rotate forwards and backwards with different RPMs, right? And now, what is our goal? We need to borrow mathematical tools from free space and make an analogy, like moving forward or backwards linearly, moving forwards or backwards in these RPMs. And we need to get quantum operators, we need to energy operator and find eigenstates. And then we can plug eigenstates into this figure and find rotational vibrational spectrum. So these levels here are rotational, these are rotational, and those two levels are ground and excited vibrational states. So rotational and vibrational work together in cooperation. And if you will be flex fluently with this figure, you will impress Dr. Herberger and you will increase my points in his eyes. Okay. And I'm not going over this slide today, hopefully Monday or even next Monday after this interview and this one. So it is our goal to get through this figure. By the way, this little figure, although I'm not speaking about it, you see same energy, non-degenerate, triple degenerate, 5 degenerate, so several states with the same energy. Before, when we were looking on orbitals for the Fusions project, we saw the same, like several p orbitals, several d orbitals, right? So we are coming to the concept of degeneracy, and this will be very important for vibration. Rotation, right, right. Good. And if you can deal with this equation, then you can write independent theoretical papers. Okay. about 12 minutes left, and it's time to start the lecture. I hope it was all correct. Okay. So it is my goal. But if I just show slides, it will be boring. So let's play near the board for a few minutes, and then the last couple of minutes I will show the missing slides. So focusing on the camera, freezing video, and prepare. I will be inviting some of you to the board. And if anyone wants to leave, volunteer. So maybe CL, here is H. We have a distance between them. We have a coordinate system. And this, they are rotating around each other.
Oh, this is like what we went over last class. So they're like, it kind of looks like it.
Oh, you're stuck.
Maybe, but maybe I was not focused enough. I don't remember it, but it will be very, very, very true,
I think
very
you're
useful. Okay, so
When the turns on the distance changes, it changes the momentum.
so momentum, distance is over r. And as we move, we increment the angle d phi. This is phi, this is d phi, this is arc length L, and this is dl. Right? So Shalevi, if we who was using sling in the Bible?
David,
Okay, is it the same?
yeah.
Yeah.
Similar theory.
Okay,
Yeah.
so biblical science. So on one hand, we can use the momentum to describe it. On another one, since it is constrained, we can use arc length as an increment. So what is arc length? Equals r5, right? So if it is a full cycle, then it is 2 pi r, right? If we do have dl r d5, right? So this little distance that the sling or HCl has rotated is distance between them times the little angle. Okay. RPMs do not have units, it's just rotations per minute, but we can use angle per minute, right? So, but there is no distance. So it is our subconscious goal to get rid of distance and express everything in angle and time. Okay. So, what else? We're not done yet, but we are very close. It's kind of a simple subject. What if we do DL? It's very simple symbols, but they will they're out of box thinking. So DL over D5 equals what? DL over D5.
And it equals R.
R.
So then you can plug that into the other equation.
Can we do D5 over DL?
One
1 over R. So which advanced area of math depends on such tricks? It is a simplest example of the very advanced math.
Like a separable equation, a differential equation.
Higher, much higher.
Oh.
Oh,
I don't know higher than that.
It's differential geometry. Like when we are simple guys, we work in Euclidean space. When the basis vectors are perpendicular and they're the same everywhere. We can imagine that they're tilted, but same everywhere. But what if basis vectors change as we travel through space? Like curvilinear space, X and Y are not orthogonal, and they change angles, right?
Oh, yeah.
Like draw a triangle on the surface of a donut.
Okay.
So it is
So
what
don't
it is.
do that.
It is what mathematicians do in this area. So, and there are all laws of the geometry that we learned in the middle and high school fail. So our Euclidean geometry is only one limiting case of more general differential geometry. And then, like if in our space we do dx over dy, it is 0, right? But there, if one does this transitions between different degrees of freedom, they're not 0. So they are metrics, they're transition between different degrees of freedom. So simple equation, but a lot of thoughts. Now, let's remember the only equation that we need to memorize from this course. So I don't remember what is the sign. I don't remember if H is nominator or denominator, but I truly remember that it is TDR. Should it be minus? Thank you. Everyone plus 1. Now,
What do you say?
Gonna write a lab report, let's do it one.
so if this deals with time constant and distance, but we do want to play game without any distances. We want quantum operators, but we do not want distances. What do we do? So if we can design momentum along this curvature, along our planes. So this is not easy. L, okay. So minus I a bar GDL. And when we write a quantum operator, we assume that it acts on a function. Now, let's assume the function depends on distance and angle. Letter phi is not good here because it's ambiguous. Let's call it psi. Psi of distance and angle. And we want to make a transition to these coordinates, distance and angle. So basic task for differential geometry. Transitions between coordinates. You did transition between like polar coordinates. It's not a big thing. And maybe you went over spherical coordinates as well. Like if I would be a good teacher of this class, I would introduce and make a lot of homework on spherical coordinates, but I hate them.
Yeah.
It is a little miss in our education for this class. Ideally, even in simple classes, it pedal to metal or hydrogen atom. Just if you go to advanced classes, plan to refresh. Whew. So I was thinking about inviting someone to the board, but I cannot miss this player. So I'm going to say is bar now. If we know that the function depends on these things, how do we do it? How do we replace derivative of this? Right. Can you try doing it? I give you my best pleasure.
It's 1 over DL with this.
Not working marker is not my best pleasure. My best pleasure is the equation.
Trying to find the number here.
Oh, but you can't have a.
In this complex.
Mhm.
This, I didn't use this method, and this doesn't matter either. I don't know what I'm doing. This is what it's.
That would just actually be that. Getting my basic.
3 generous minutes for the whole remaining lecture. Okay,
I guess I
Good,
just.
right?
put one thing.
so B.
Oh, that
If
is
the,
what you were
if the,
trying
if the
to-
function depends on distance and angle, we need to dr of phi plus d phi of psi. Somewhere, would you be permitting me to read this one?
Yes, yeah.
Okay, thank you. But in order to practice this appropriate derivatives, we need to d r over d l, right? So that if you cancel this and this, it will be ddl, right? And here, what do we do? D phi over dl. Okay, you agree?
Yes.
Now, we can temporarily, or as long as assume that we work with rigid rotator. Rigid rotator. And then this derivative will be 0, and we can neglect this term and do things simpler. Now, what is d phi over dl?
1 over R.
Okay, so we have minus I h bar 1 over r d phi. So it is our momentum along arc length, right? We still have the r. I will take maybe 1 or 2 minutes, but I understand that we need to do that.
Don't you just like substitute it out?
What is angular momentum?
It's like, it's how much the
Definition.
angle changes over time.
Right, but vector of angular momentum. Cross product.
Mm.
We need to.
Oh, so you can't just substitute it.
So what is cross product for angular momentum? What do we do cross product of what? Raise hands if you know what I'm talking about and show it.
I'm not pulling it up in my brain.
So on the melody, right? Try your best. Quickly. Because we only need
It's angular momentum.
angular momentum is a vector perpendicular to the plane of rotation, and its length is equal to. If you were taking like freshman physics, which is I think is required.
Yes.
It
You
exists in
had
my brain. I can't
You-
remember it.
So say that one more time.
Okay,
Angular momentum is L.
L, angular momentum. What angular momentum is a cross product of two vectors.
Yes.
What are those two vectors?
Your angular is gonna be your rate of change of, it's your momentum cross product with your,
Are you having A in all classes?
yeah.
Is here correct?
I don't know what grade.
Did you hear Sam?
It's momentum cross product with your. No, because momentum's gonna be going.
Position.
Yeah, position.
Oh,
Okay.
P cross R.
Yes. So P, if you do have this rotation in the plane, so P cross R vector, and then if you be vector L here. So I'm finishing. If we speak not angular momentum vector L, if you do have L defined as R times P, and if you have only one plane direction, it will be just operate R times P, and you want an operator, then we have minus I H bar R times 1 over R d phi. Can we cancel R? Yes? So you get minus I H bar d phi. What a wonder.
Yeah.
So no masses, only Planck constant and angular momentum. This is something that you may want to remember in the middle of the night as well.
Okay.
This operator of angular momentum is a foundation of Bohr's model and rotational motion. Quantum mechanics started from angular momentum.
Hate to be that guy, but we gotta test it.
Okay. Can you please show that meeting? Just a second, just a second. Yes.
Meeting is
Meeting is done.